Hello, everyone. My name is Pablo Castro. I'm a researcher with Google, and I'll be presenting the paper with Johan Obando Ceron entitled Revisiting Rainbow. What we argue in this paper is for the value of small to mid-scale experiments for deep reinforcement learning, as we believe they bring two important aspects to the community. The first, it makes the community more welcoming and inclusive of people that don't have access to ample computational resources. And the second, it enables broad sweeps of experimentation that can lead to new scientific insights. So to do this, we revisit a paper from a couple of years ago, Rainbow. And in this paper, what the authors did is combine a few different existing algorithmic components into one new super agent that was state-of-the-art at the time, called Rainbow. And so the first thing we did is evaluate what was the cost of this paper. So this paper was evaluated on Atari games. Each Atari game takes about 5 days to train on a P100 GPU. There are 57 games, and if you run 5 independent seeds on each of the games, that means you're running at least 34,200 GPU hours, or close to 1,500 days. Given that a P100 costs about $6,000 to purchase, this is a very expensive experiment to run, and it's quite limiting as to the types of labs that could run this type of large experiment. To put things in perspective, the average minimum wage in Latin America, excluding Venezuela, is $313. So that means that a single GPU would be about 20 minimum wages. So it's a very expensive experiment to run. And so what we asked ourselves is, what if we were to revisit this Rainbow paper and rerun the experiments there, but on smaller environments? So we did this with 4 classic control environments: Cartpole, Acrobat, Lunar Lander, and Mountain Car, as well as a medium scale environment, which is Minotaur. These are miniaturized versions of Atari games. So as I said, Atari games typically take about 5 days to train. These Minotaur games take about 10 to 12 hours to train. The top environments, the classic control environments, don't require any convolutional layers, whereas the bottom environments, the Minotaur games, do require one convolutional layer. So what we found is, overall, we reached the same conclusions as the Rainbow paper, even when running with these smaller environments. So the conclusion is that the Rainbow agent is best when combined with all of the algorithmic components. One interesting finding is that DQN plus distributional, without any of the other components, does not perform very well in these classic control environments, as you can see in the green line here. So this is quite interesting, because this is not something that was observed in the Rainbow paper, and I'll come back to this in a little bit. When we did the ablations, however, we did find that removing distributional had a pretty big impact on the performance. So that means that distributional for these classic control environments, just on its own, is not enough to give us the boost to DQN that we require. It really needs to be combined with some of the other algorithmic components. Interestingly, in the Minotaur games, we don't see this phenomenon where DQN plus distributional doesn't perform very well. Here, we do see that DQN plus distributional performs quite well. So this suggests that perhaps there's some correlation, not just with other algorithmic components, but also with convolutional layers. Given that Rainbow was only run on networks with convolutional layers, this opens up a new set of questions as to when do distributional methods perform best, and with what type of network architectures. So this is starting to give a glimpse into the types of insights that we can get with with experiments on these smaller scale environments. So we also went beyond the Rainbow and started asking some new scientific questions. So for instance, revisiting some old assumptions, DQN is traditionally run with the Huber loss, and this is not something that anybody really changes, but we decided to experiment replacing it with mean squared error loss. And the results were quite surprising. We found that across the board, we get much better performance with mean squared error on both the classic control and the Minotaur environments. And since then, we've run experiments on the full Atari games, and we find the same behavior. So this is something quite interesting that we'll be looking into further. We also ran the Rainbow experiment, but with quantile regression rather than C51. And we found overall the same kind of result, that it's best when combined with all the different algorithmic components. However, an interesting thing we found is that quantile does not perform well with dueling networks. And so this is something that was quite surprising to us, and we're looking into to understand more deeply. But this is another one of these scientific insights that we were able to get from these small to mid-scale environments. So thank you very much for your time. We're very excited by this work, and we hope that this type of work will open up the door to people from all sorts of communities and all sorts of geographies to do meaningful and impactful deep reinforcement learning research. Gracias.